Hi, good morning, good afternoon, everybody. Welcome to Tech Talk Live. My name is Kristen Castaldo. For those of you I haven't seen before, I'm the Director of Self-Service and Community here at IFS. Just a heads up, this session is being recorded. We will share it to the community after the event. We will take your questions at the end. Feel free to drop them in the questions widget or in the chat channel. We do have some employees online who could help any questions you might have during the event in the chat channel. If you haven't attended a Tech Talk Live before, they're part of our success sessions. And these are sessions that we host almost monthly for our customers, partners, and employees. They cover a variety of topics. Sometimes it's a product overview or a demo. Sometimes it's Q&A with like IFS leadership. We publish these in the community, so you're able to check there and see what the next one coming up will be. Today, we are covering artificial intelligence in IFS Cloud. We're joined by a couple of our data scientists, Justin Charbonneau and Karan Tandon, and then a data engineer, Jayson Crasto. So they are going to give you an overview of artificial intelligence in IFS Cloud with a demo. So I will hand over to you guys. Again, if you have questions, please just drop them in the questions and I will read them out at the end. Thanks.
Thank you, Kristen. Okay, so to start things off, I figured we could introduce ourselves. So today you will be hearing from Karan Tandon, who is the lead data engineer with a background in the aviation domain. He is part of the R&D platform automation team, as are all of us. Then we have Justin Charbonneau, who's our data scientist. He comes with a lot of expertise from the retail, banking, and marketing industries. And finally, I'm a senior data engineer on the team with several years of experience in the aviation domain as well. What we'll be covering today are a couple of topics. So we'll be looking to start by introducing artificial intelligence before we then start reviewing the asset management use case. And then we'll move on to sharing our development journey and how we've built the product around it, before finally closing off with where we intend to go next with AI. And with that, I'll hand over to Justin for the introduction to artificial intelligence.
Thanks, Jayson. I'm just waiting for the...
There you go.
Perfect. So yeah, so I think I'll start with an introduction to AI. And doing so, I'll start with a few definitions.
Hang on just a second. Let's, I'm seeing the success session screen. I don't know if you're sharing your presentation now.
So I clicked the yes.
Okay, I've got artificial intelligence on the screen now. I just want to make sure you didn't change to a new slide and we missed it. There we go. Okay, got it. Okay.
Awesome. So what is AI, machine learning, and deep learning? These terms get sometimes interchanged. They appear often in the news. So let's go over them. So AI is like an umbrella term for the science that studies ways to build computer algorithms that learn and solve problems in a similar way as some human cognitive functions. So you could think of the act of learning or decision-making tasks. So this is different from the human or animal intelligence that you might think of. Machine learning is a subset of AI. It's a major component of data science. In fact, machine learning lies in the intersection of math and computer science, where you'll have a set of algorithms that can learn from data without being explicitly programmed. So you can use these machine learning algorithms to generate some insights from the data. So when we say that we're using or doing machine learning, what we mean is that we're using computer algorithms, statistical methods to help the computers learn and make decisions without human supervision. Then we have deep learning. So this is a subset of machine learning where these algorithms learn from a hierarchy of concepts, which is similar to how the human neural system works. And this enables the computers to learn really complicated concepts by building them out of simpler ones. So if you were to draw a graph, show these concepts, how they are built, you would see that they are built on top of each other. The graph would be deep with many layers. And this is really the reason why we call this approach to AI deep learning. Now, I won't be diving into deep learning in this talk, but I have a quote here from Geoffrey Hinton, who claimed that deep learning will be able to do everything. He's a pioneer in the field, and that's, I think, one of the reasons I thought it would be good to include as part of the definitions. So you might be wondering, how do we train these algorithms? Because I'm saying that we're training them without any human supervision. And the answer is that we need some data. Now, data can come in many forms, could be images, text, audio, sensor data, you name it. But here today, I'm going to be focusing on time series data. Now, often sensor data comes in the form of a time series. And one particularity of time series data is that the data has equal intervals between them, and the future values will depend on the historical values. So what's the difference with data and the data set? Well, the data will be the observations, the raw measurements, and then that data set is going to be a structured collection of that data. So in this example on the screen, on the left, you have numbers, the raw measurements coming in from a sensor, and that data set is that structured collection. So I've got 2 columns. There's a timestamp for each sensor. They're sorted through time. And once you have a data set, you can train an algorithm. And so once you have a data set, you train an algorithm, the output becomes a trained model. And that algorithm trains because it's going to be using that data, making some predictions, looking at the error given the ground truth, adjusting its weights and parameters, and doing so iteratively over and over again until it's finally trained. So here, yeah, the takeaway is just that passing the data set to an algorithm, you obtain a trained model. So once you have that trained model, what you can do is pass in some new data. And that's typically called making inferences. So once you have this new data, here I include an annotation on the left columns, where current time is typically denoted as time t0. Previous time step, we would refer to time t-1, t-2, and then in the future, we refer to t+1, t+2, and so on. Now, usually what we do in time series forecasting is that we'll generate one prediction, which will be a single step forecast. So if you're using daily data, you're going to be predicting a value for tomorrow. But we can also do multiple step forecast. There's no issues with that, but the only thing to consider is that the more time steps that you're projecting into the future, the more challenging the problem becomes, because there's a compounding nature of that uncertainty of each of those forecasted steps that you add. So now I'll talk a little bit more about time series. So what makes time series a bit different from other types of data? Well, when you plot time series data at the top plot here, you would see that it exhibits one or more of the features that I listed below. So you'll have a trend, which is the general direction of the observations. You'll have some seasonality components. So those are variations into your data that will occur at specific intervals in time. And you can have events and impacts. So if you were to think about the use case in a supply chain, recurring events like Black Friday would inevitably trigger a big increase in your demand. So you have to model all of these different components. These are actually more of like some basic characteristics. In your seasonality, you can have multiple seasonality. It doesn't have to be just one. So you could have really granular seasonality at the daily level, at the weekly level, or even at the seasons. So summer compared to winter. But when you think about time series, often all of your use cases will come down to 2 main ones. You're going to be doing forecasting, or you're going to be anomaly detection with these time series. So this forecasting problem, I already talked a little bit about this. What we do is that we split the time series data into some fixed time intervals. The first portion would be used to train your model, and the later would be used to forecast and evaluate your different models. And this is how you determine which models perform best and which don't. So it's pretty straightforward. And so within that training data on the left, you identify patterns, but there's also one more thing to consider, which is determining how much data do you provide to your model. So do you use, for example, 1 month of data to predict the next few time steps? Do you just use 1 week or even just the last 24 hours? And all of these decisions will vary depending on the data that you have. And especially if you're including additional sources of data. So let's say you're looking at sensor data, you might have multiple sensors for a specific asset. Well, you'll surely want to include all of this data to help your model identify these patterns. And finally, one more thing about forecasting is the intervals in which the data comes in will be the same intervals that the model outputs. So if you're using historical daily data, your model is going to be predicting daily data as well. So we've talked a lot about forecasting, which is one of the major areas in time series, but we can also do anomaly detection. And anomaly detection is the process of finding data points within a data set that differs from the rest. And there's many challenges to anomaly detection because usually your data will contain a lot of, or mostly, normal observations. The anomalies are rare. The anomalies can also be really different each time. And it could be either you have one single point as an outlier, or it could be you have deviations lasting for a long time. And all of these decisions of what consists of an anomaly could depend on the use case. So since we don't have really a lot of data, or we don't know which data in our data set is an anomaly, we can do unsupervised anomaly detection, meaning that we don't know which data points, right, are anomalies. And we're going to be focusing on learning what is a normal behavior. And once we know exactly what is a normal behavior, we should be able to spot something that's being abnormal. So what we do is that we'll train an algorithm that's capable of understanding normal by providing it only normal data. And so if there ever is like an outlier, a spike in our data, your model should be like, oh wait, what is that? Like, this is going to flag it as an anomaly because it's really a strange behavior that it hadn't seen before. Now, this is really useful because once that model is built, it could be used repeatedly to evaluate in production and detect anomalies on new data that is collected. And this is really, really great. So I hope this will give you enough context that you'll be able to follow along with the actual industry use case. And I'll pass it on to Jayson as I'm making him the presenter.
Thanks, Justin. Okay, next I'll be covering asset management. So just following suit from where Justin left off, I'll start with what I mean by assets. So in this case, an asset is referring to machines. In the case of airline operators, we'd be referring to aircraft, MROs, APU, landing gear, and the like. But for the sake of the presentation, we'll be focusing on wind turbines. So later in the presentation, we'll show you some data that we've put together for wind turbines. But the whole concept of asset management in this case is to address asset failures well before they happen. So through preventative maintenance, that is traditionally how it's addressed. But as we know, asset failures can be extremely costly and stressful for businesses. So the ability to shift from preventative maintenance towards a predictive operations is key while being able to find the right balance to maximize operational effectiveness. So that's what we try to achieve through 4 key areas. So as part of the data journey that we try to produce within IFS Cloud, we start off by looking at data collection. So where can we pull information so that we can start down this journey of predictive maintenance? So we look at raw telemetry data that we could access through IoT tooling. Then we try to move towards intelligent engine. So it's trying to build the model that Justin alluded to earlier, so that we can then determine forecast models or whether it's anomaly detection and the like. It's trying to address the visualization problem through IFS Cloud. So displaying the information that we can retrieve using those models, so that businesses, users can then use that to make informed decisions and then help drive the optimization of those decisions through IFS Cloud, through the likes of Workflow Designer, amongst all the other features that IFS Cloud has to offer. That in general is how we're looking to approach the asset performance monitoring solution. And with that, I'll hand back over to Justin to share how we've kind of gone through the development journey. And with that, Justin, back to you.
Thanks, Jayson. So at this stage, we're really at the before going into production. All right. So the development journey, what it looks like for data science and machine learning, well, it's an iterative process that we go through to get a really better understanding of the problem and find what is the best solution, which in this case would be the best algorithm for the given use case. So you can think of all of this work, more of offline work before we move into adding that solution to our product. And throughout these different stages, the work is going to involve data scientists, data engineers, machine learning engineers. So the whole team is helping out. So it all starts with some data. We take a snapshot of data, real data, store it in a secure way so we can access it later. For long-term projects, it could also be good to take snapshots every so often because that data is ever evolving. So now that we've gathered some data, we start cleaning it and we are focusing on really understanding the problem. One great tool that we use are Jupyter Notebooks. Jupyter Notebooks is what you see on that similar fake laptop. And then it's an interactive computing platform. And so my personal preference is coding Python. And so this notebook will combine my code, some text, equations, visualizations. It makes it a very powerful tool to iterate quickly when you're working with data and share insights with the team. Now, also at this stage that we're going to have defined some assumptions, some about the data, some about the problem, and we can even start validating a few of them. So is the data coming in at equal intervals? Do we have any missing data? And if we do, we might impute them. And so we start manipulating, cleaning, dealing with missing values and other operations like that. It's also important to research the literature because domain understanding is an integral part of machine learning. And it's important because some of the assumptions might be domain dependent. So you'll be looking at the variance in your data, the independence, and other assumptions. Now, usually at the end of this stage, what we'll have are a clean basic data set that we can work with. And then we'll jump into exploratory data analysis. Now, here we're trying to identify patterns and understand the data. So we're going to often be generating many visualizations, heat maps, plotting some data points, looking at the different granularity of your data. You might be partitioning it to view different views of the data. You're going to look at the correlations in your data and all of that good stuff. So even here, I'm using a Python package called pandas profiling. This is just one of the many visualizations that it generates, but it generates them into that Jupyter notebook. So here I'm just looking at sort of like a heat map between the load and the day of the year, but you'll already see some sort of patterns or like a cyclical pattern at the yearly level where probably in the summer it has a different behavior than in the winter. Now, generally what you try to do here is tell a story with that data. So you use that Jupyter notebook, go through all of the few steps that you've done, loading, cleaning, visualizing, trying to identify some key takeaways. You can even use, you don't have to use, for example, Jupyter notebooks. You could connect it to Power BI or other dashboarding tools. In the end, it all boils down to what you're most familiar with. But this initial insight that you're having on that data will help you decide which types of models you should be planning on using. There's an abundance of algorithms from machine learning to deep learning, and you have to scope down which ones might be the most promising. And not only that, but this also helps you identify some feature engineering steps. So that's sort of the process of transforming that raw or clean data into additional features that your models could be using. So now let's jump into modeling. Well, the first type of model should be your baseline. But what is a baseline? Well, it's a simple yet reasonable, it should be fast, repeatable algorithm that sets the stage, so that minimum expected performance on a given data set. Now, typically a baseline has no machine learning. It's super naive. And so if you were to think of two different use cases of how you could find an appropriate baseline, if your data is exhibiting a lot of seasonality and multiple seasonalities, so at the weekly, at the seasonally, even yearly. And so what you want to do is capture that one full period of seasonality. So you'll offset by that longest seasonality. And so the baseline here could be simply predicting a repeated year. So what happened a year ago plus 1 day is what's going to be predicted for tomorrow. Now, maybe your data is trending more upwards. Maybe there are or not some seasonality. So then you can have a more naive forecast, which you could be just using the value of yesterday to predict tomorrow. So use t-1 to predict t+1. And those will surprisingly sometimes surprise you how well they actually perform. And they are very, very simple. So once you have that baseline, you're going to start exploring different types of models. But like I said, there's so many different types of models, and often you're collaborating in a team. It can get quite hard to track all of your different experiments. So here, that's what, in this offline work, we use an experiment tracking tool. There are many tools out there, and this allows you to get an overview of your experiments, and it's structured, and it's great for collaborating. And so in these experiments, what you'll have is a collection of runs. Each of those runs will be the act of training a model and evaluating it on a given test set. And there's a lot of information that you can store in these experiment tracking tools. You could store the time it took to make the predictions, time to train, the actual model. You'll store probably the predictions so you can take a look at them later, parameters, metrics, and anything that you'd like. So often in time series, you also do backtesting. So you're going to evaluate your models on different time horizons. So you don't want to just split your data once and hope and use that information to choose your model. You'll be want to running that experiment multiple times throughout maybe the year or over a few years and aggregate all of that information. And this is where it becomes really beautiful when you're using these types of tools, experiment tracking, and doing your data science work, because then you can pull everything back into that Jupyter notebook and do a deeper investigation. Look at the errors. Are there any bias in your data? If you did adding additional data actually help the model or it hindered? And you can really dive deep into that. So now that you've done your due diligence in research, modeling, you have a good idea of how the models are going to behave, you can move on to deployment. And at this stage, what you should know are types of data aggregations you're going to be performing, what types of data cleaning routine you'll need, what types of algorithm do you think you'll be training, and probably how long forecast do you want to predict for. But there's also one more thing, and it's knowing when to retrain your models. So I've previously said data continually evolves, and this phenomenon can be called data drift or concept drift. So your model's performance is going to deteriorate over time. And to mitigate this, it's pretty simple. You could simply retrain your model. Now, for example, if you had a technician that changed a part on an asset, that might have altered the behavior. So maybe they added a better cooling system. And now that temperature that is being tracked in one of the sensors is generally lower. And that's going to offset sort of what the model is expecting as data. It might affect the performance of those forecasts, or it might even flag it as an anomaly. So there's different strategies that you can take for this. You could be monitoring your model, storing the errors, looking at real time, and if at some point your errors are starting to increase, well, you'll trigger retraining. Or you could set a retraining cadence. So given all of your findings that you've done offline, you might already know that you'll have to retrain your model every week, or on every Sunday, or every month. So I hope that you've enjoyed this of the offline journey, and then I'll pass it along to Karan, who's going to taking you into a more deeper actual product.
Thank you, Justin. I hope you can see my screen. So based on all the understanding how the model is being trained and what is training, inference, prediction processes, and one of the use cases Jayson mentioned that we work on is asset performance monitoring. This one, I will walk you through the entire data journey. Means data is coming from the sources, IoT Central, and all the way into our IFS lobbies as a dashboard. So we have simulation of some data. Essentially, we have pre-recorded video that I will walk through. So essentially, in this one, we have some devices created around the wind turbine. So we have two machines, machine 1 and 2, and they are essentially based on the template. So we define the one template, what are the parameters of it, and then we can create as many as devices we can create it out of it. And also we can do the grouping and create the classes, and so all the configuration would be the similar for based on the group. So essentially, these are the blueprints, devices templates, they're also called. And if you want to look into the specific machine, how it's being generated. So it's a simulated data that is being generated about every minute or a few seconds apart. And within that one, we have some variables in it, which will be we do some forecasting and use as a predictors. So we have the timestamp and some device information within with the payload. We have inbuilt utility, data export. We'll be exporting this data. That will be the dumping data into one of the storage layer, which is the data lake. So as the data comes being generated, it just comes into our data lake. So essentially, data lake, it is a storage layer. We save the data in the file system, and we have a structure in a way we create the container, and within that we have the file system hierarchical order. So the way, as you see, this one, this is the application ID of the IoT Central. In this one, if we go within that one, we have the two devices set it up. This just come auto-generated IDs, and within that we have the datetime the datetime format, the actual file, which will be data is being generated. If you look at the file, essentially we have the device information, the time, and also the telemetry itself, which has all the variable in it. And so moving forward from here, we have another sources of the data, which is we call it landing. So landing is the data essentially we will be using for, let's say, we have for the training processes that's Justin was mentioning, we need to have some certain number of the data points. Telemetry, if it is plugged in today, we won't have enough data points. So we use the landing data, which we could have the historical data for past 1 year, 2 year, or so on. And for this exercise, we have loaded the two machines, exactly the same way of the structure that we have defined in the IoT Central. And then we have another setup. We have raw, silver, gold. This is a different zones. So how we do the transformation, we move the data into different zones. Gold is the final stage of the data, where all the final data set comes in, and we have some of the configuration set up here. The configuration, essentially, it is for all the models that Justin touched upon. We have anomaly detection and the time series.
So these are specific to there's some configuration that's like time sensitivity and those kind of information those configuration go within the anomaly detection, and with the time series we have some time series specific configurations. We have some common configuration that we've been used for the pipeline and for our ML processes. This is essentially the idea is that this will be exposed to the end user, which essentially they can choose the specific model if they want to choose for the time series. Essentially, we have currently baseline model, our profit algorithm, or we want to go to ML service as a general, and we have for anomaly detection what are the models that specific can be chosen. And we have some then target variables. What are the variables that we wanna monitor? We wanna get the prediction norms, and that can be defined here. And then we have predictors. What will be those variables that will helping us to predict those targets? At the bottom, we can also we can set up the horizon, like the length of the forecasting that we want to choose, and same go for anomaly detection. Some parameters like the sensitivity of the anomaly that can be also set it up. The frequency of the data set, whether it's a daily or hourly or minute, but in this moment we will convert into minutes into hour frequency, and the aggregation that we apply as a mean. And then there's some error handling, like if it is a failure in case we want to retry, or those kind of mechanism can be. And then we have the source as well. The first exercise, the demonstration will be running. It is the landing data that we want to run. It's about a year of data. We'll be processing the landing data. And yeah, now from this point, we'll jump into our orchestration tool. Essentially, this will allow us to essentially trigger those our pipelines here. So this is our orchestration tool. On the left side, we have the pipeline, which is the APM specific pipelines. We have some core pipelines, and we also see some ML specific pipelines. Once we execute those, we can monitor in this section, we can monitor the pipelines, how they're behaving, what has been done in the pipeline. If they're through any failure, it will point out to any failure, or the retry mechanism is available. So from here, we'll just go ahead and run the pipeline. Essentially, we're providing, so the data is the way we set it up. It is the historical data. The end date of the historical data is 2 days before this meeting was recorded. And essentially, the class is the grouping. We want to put into all the devices into one specific group, and the problem type, which is we want to do the time series forecasting. And we'll just go ahead and we'll run the training pipeline. From here, once it's triggered, we can move to the monitoring section, which will essentially will provide us the information what is being done at this moment. So from here, we are doing the preparation, movement of the data, essentially reading the data from landing, moving the data into the raw. So from here, it takes a few time in a fast forward manners, and this is what will be the end result here. So what essentially we did here, moving the data into final stage into gold, have been reading through all the configuration, what is required, whether it's time, what model that we want to choose, what is the frequency of the data that we want to set it up, have reading that all configuration, we have the final data set, and then we have the model trained in the end. So if you can look into the data lake, we can go to the gold like row section. Here we have when we copy the data from landing to row, and we have the timestamp created. This was essentially the data, the 2 files that we have loaded, and then similar fashion we have silver. Silver essentially we keep the data and we apply some aggregation. So the final, so we have the devices list, which is the unique devices list, telemetry. Within telemetry, we will go through the data and do the partition up to year, month, and the day level. And within that, we have the classes, devices, and all structure formatted. So this is the last day of the data is the 24th of May, and this is where data ends. And then other stage, we have finally the train data. Train data is we store as the aggregated data. So data is coming every minute, but we store, we apply the aggregation, and the data will be apart, essentially 1 hour apart. and we applying to the mean. And if you want to look into the file as well, the data will be just sort out, increase the length of the data set, and sort by timestamp, which will starting from the May 2021 and all the way till May 24, 2022. From here, now we are pretty much ready for our next processes, and just to see what will be running on the predictions, and we'll see the model first. So we have created the class. The class one is as a grouping we have passed, and the devices are created. And then for time series model, and we can see some logs in the during the pipeline generations, and then we see the model. Model we are storing as a pickle file for each model. For this device, we are targeting 2 variables, and then we have some configuration but this is an offset essentially. So this will allow us to just provide a recent trend when we're doing our inference or prediction call. Where we pass this offset the last few data points of our training data set, which will give us a recent pattern and to get the better predictions. So these are the information that we pass in during our predictions, offset, configuration, and the model itself. From here, we can, I think we are good from this point. We just need to, what we would do, we would change the configuration to the IoT Central. So we will get some more data that this will be the real-time scenario that will be fetching the data from IoT Central of the last day. And then all that we need to do at this point is just change the configuration. So we go here, and the source now, instead of landing, it will be the IoT Central. And here we just apply the information of that specific location. And from this point, it will allow us to now fetch the data from that hierarchical order of the IoT Central. Such these 2 devices will be fetching the data. And now from here, Data Factory, we'll do exactly the same way, trigger the pipeline, but this time we'll be running, the request type will be the inference request, which will be essentially running for the prediction. And we'll just type in the inference, execute that pipeline, and then we can, from this point, we can start monitoring what is doing behind the scene. So from monitor section, we see here the main pipeline is executed, and we'll do some fast forwarding, and we'll show that what are the pipelines actually executed. So from this point, we are running essentially we copying the data from IoT Central folder, and then processing it, aggregating the data because it's minute and changing to hourly, and then running our ML service pipelines, which will get some predictions, and those predictions we will essentially push into IFS apps in the end. Those are the PL execute push. Those are the pipelines just to push into IFS apps. So these are all the pipelines around our inference. So from here, we will now move to the data lake, and we will see what would the behavior in our data lake, what change. So the row, first we look at the row, we will have the data that is, we say -1, essentially it's the 25th of May, and we got the 1 day of more incremental data. And then we look at the silver, and silver, the different thing will be this time we have the essentially we have the inference data set. If you want to look at telemetry, we will be looking into 1 day of incremental, and we're targeting the day 25th of May. And later we can also look at some our other data set, that is the inference data set that we prepared. Again, the data format will be in the Parquet format. As we're getting more inference, we do the incremental on that file. The final stage, again, is it is the gold. Within the gold, now we will see more information, the prediction information, along with the model itself. So from here, we have the inference data set that we copied essentially from the silver. And how our data looks like, essentially based on the offset, as I mentioned earlier. So offset is essentially providing the model the recent pattern of the data set. And about offset was about 336, and this is the data set, the recent data set we're providing, including not only the historical data, but also the coming data from the telemetry from IoT Center itself. And this will be passing to them our machine learning surveys, and finally we get the model predictions, and then for the specific temperature gearbox. And these are some of the timestamp and some of the predictions that the horizon that we have declared in our configuration file. From here, we next step is that we move to the push prediction, and now we can see that how the predictions are in the IFS apps. And here, with the prediction, if you go to the specific detail, the way we are sending is as messages. We are sending, if we go to the detail here, and we will like the timestamp so it's the rows, we change the column, each timestamp with this actual date and the device information, and the model itself, what model that we're passing. This model is a time series forecasting, but we'll have the later more models. So this is the journey for the time series, and the next thing would be if you want to now change to anomaly detection as well. We already have processed the data. We have the data in already. We don't have to copying the data anything. It's just we need to run on the same data set. We'll run our anomaly detection pipeline. Essentially, we first again step is we go with the training for the anomaly detection. We execute the pipeline, and they can be moved to monitor section. And essentially, it will be much faster because there's no copying data processing involved at this moment. It's just getting the data, just calling our ML service. So yeah, this is ML service final stage. All pipeline being executed, and we can now jump into actually the data lake and see what is being created here. Data-wise, nothing changed. Rows will remain the same, and we can just move to the gold. And within the gold, we see classes. Now we should see another folder, which is anomaly detection. We will have model trained, some logs, and the model will be specific to all those two variables. And the training data set is essentially the same that we use for time series. So from this point, we can now run actually the detection. Now we can some detection or predictions or anomaly models that we just recently created. For that, again, the last step will be exactly the same way. We just need to be straightforward. We need to make sure we change the problem type to anomaly detection and the request type to inference. And the -1 is essentially the same data set that we have already in place. And here, from here, we pipeline and see the behavior, what it will be do. And the pattern is exactly the same. We will train the model. We'll be on the train model. We run the predictions, and predictions are, and then those are pushed into IFS. And the pipeline has been fast forward executed, and yeah, from here we will look into how the data is being stored in the data lake. We go here, data lake, look at the gold, and now we have another folder created, which is for anomaly detection, which is really predictions. We look into those predictions. Here so this is the inference that we have sent based on essentially the offset or the inference that in this case is really the inference that we want to get the prediction on. So it's about 192 rows that we want to get. So this is essentially historical data. So that's the difference between forecasting and this one. We're getting those anomalies on the historical data. So now we look into those data set and we pass to our machine learning surveys. Essentially, we'll get essentially, yeah, we get to those. So it's a 0, it's a normal behavior. If it's equal to 1 or more, and that's anomalous behavior. And having this information, yes, let's push into IFS apps, and then we will we'll look into the actually how it's looking in the dashboard. So our dashboards, they are connected to essentially our data lake directly, And we show here our wind turbines, 2 wind turbines that we have, 2 machines. We set it up, and 2 machines then have 2 parameters, power and temperature gearbox. On this page, we are looking at parameter values on the left, and the bottom we have the time horizon for about 3 months of historical data, and we see here peak here, and that here our model is detecting this is anomalous behavior, and in red we are doing some forecasting of what will be the behavior after it will move to the normal. On the left, yeah, we're mentioning about what are the like in the past week, how many anomalies has encountered, and what are the planned work orders that we have in the middle sections. And yeah, so that if you have any planned work orders or any work order done, and that will also show in the graph as a different indicators. So that's the essentially end-to-end pipeline, the flow, the journey of the data. And then, yeah, I will move back to Jayson.
Thanks, Karan. If you can make me presenter. Awesome. Thanks again, Karan. So the question is, where do we go from here? So at IFS, we are researching innovative ways to catalog data. We're starting with looking at using graph technology and enriching knowledge articles. We are also testing cognitive services that will support bot and communication channels, as well as visual inspections using AI. So we intend to try to identify defects and through an automated process, trigger the appropriate responses to ensure that those defects are addressed. In addition to that, we're looking to build on what we've already set up so far. So we're trying to build in explainable AI, being able to describe in an effective manner the reasoning that's going behind the predictions that are being made or the forecasts that are being made in a way that shows that it's not biased or by any means affecting the results based off the data that's being passed through. We're also looking at new graph algorithms if they're beneficial to us, along with context awareness, amongst several other things. In terms of the autonomous execution, we're looking at improving and hardening the workflow execution process that we have and trying to build in a feedback loop if at all possible. But those are some things that we're looking at amongst others. We're also looking at initiatives at a higher level. So within IFS Cloud, we are trying to find and identify IFS classes where we can build in clear business value from day one. We're trying to build this to be out of the box solution so that users can have access to it immediately, while still being able to drive intelligent decisions using the knowledge that's already there where they need it most. We're trying to identify scenarios in the future before the business may face some of those problems, while also being able to deploy this in a no-touch manner, so with very little interaction from the customer beyond interest to review and work with our tools. And with that, I close things out. Are there any questions at this time?
Well, thank you guys for the presentation. I'm monitoring the question channel and the chat channel if anyone wants to drop anything in. We haven't had any so far, but it might. It's a lot to take in. So people may have some questions after the fact. I was about to ask if there a way for people to be involved in this, but that's kind of the point, right? Is that you collect this without much interaction or feedback from customers directly.
That's right. We're looking to be data driven, so it's using what's already available within the system.
We've got some feedback, but no questions. Just I'll pass some feedback on to you guys about how it's fascinating, the work that you're doing. This session is recorded. I will put this in the community. If you happen to have questions after the fact, you can drop them as comments on the post in the community, and I'll let the guys know as things come in. Yeah, thank you everybody for attending. I hope to see you at the next one of these. Check the community events section to be notified of our next session available. Once again, thank you guys.
Fantastic. Thanks, everyone.
Thank
Good
you.
one.
Thank you, everyone.